Hello guys, for this video we're going to be using the node attached in Canvas, and today we are discussing similar figures and how we're going to be using proportions to analyze similar figures and find missing measurements. Alright, let's take a look at our vocabulary terms. So first of all, what is a similar figure? Similar figures have the same shape but different size. So yes, we're going to take a look at two triangles at the same time, or two rectangular shapes, or two pentagons, and so on. To be similar, okay, super important. It is a very specific qualification. We have to make sure that corresponding angles are congruent, and corresponding sides are proportional. Let's take a look at this example that we have in front of us on the side right here, and go ahead and really focus on what does it mean corresponding angles are congruent. What does it mean corresponding sides? So corresponding angles are angles that are in the same position but different location. These two would be your sets of corresponding angles. They're both these two obtuse angles. So when we talk about their relationship, we would say angle E is congruent to angle B. So the symbol that I'm drawing, it's two lines and the little squiggly. That represents congruent. And I hope you guys are remembering that the special marks, so one mark, two marks for angle D and A, so that shows their relationship. They are congruent to each other. And then C and F, both of these angles are congruent to each other as well. So they are in the same position but different location. And they're always going to be congruent. So think of, if you wonder like, well, one seems to be larger than the other. That is true. The shape may be, or most likely is, a different size, but the angles always have the same measure. Just think of, guys, the building that you are in right now, or your room at home. Without 90 degrees, they cannot really be structurally safe. But at the same time, we also can have a 90-degree angle on our paper. So that is a drastic difference in size, but your angle measure is still absolutely the same. So we talked about our angles. Now we're going to take a look at our corresponding sides. So again, just like with angles, the sides that called corresponding are in the same position but different location. So the sides that we're going to be talking about and analyzing, so for example, these two sides, and I am wanting to use a bright set of colors to just kind of show you guys the similarities and the differences. Again, same position, different location. So then I will just do like a squiggly line for this and squiggly line for this. So when they're asking you, give the corresponding sides and their locations. Sometimes you are simply asked to write down the ratio. So for example, just like I've mentioned earlier, I would say EF is related to side BC. Okay. And then I would say DF, the little squiggly one, DF, not E, DF is related to side AC. And the last little bit that I have here, this one right here, it would be DE, so no marks, is in the same position as AB. So corresponding sides are going to be proportional. Let's talk about, guys, that proportionality. What does it mean, proportional? So what I'm going to do right now, guys, right below, I'm going to enter the measurement. So EF was 9, BC is 6. DF was 15, AC is 10. And then we have 12 and 8. You might say, whoa, how come we put in the equal sign between all of these three ratios? Let's reduce them, guys. I know right now it does not seem like they have any kind of relationship, but if we reduce every one of these ratios by their common multiplier, so for example, 9 and 6 both divisible by 3, so that would be 3 over 2. 15 and 10 both divisible by 5. So when we are dividing both of those measurements, we're going to have 3 over 2 and so on. So this is the ratio that is consistently true for all of them. So that is your proof that these sides are in proportional relationship. They correspond inside, they're in a proportional relationship. That means these two triangles are similar. Okay, so we have proven using both of those characteristics. We're going to go back, guys, to the beginning of our note and going to talk about the ratio of corresponding sides. So we've talked about this earlier, just a second ago. We have set them up in a corresponding relationship. We have reduced our measurement, and we came up with the ratio of corresponding side. What we determined, guys, is the scale factor. So hopefully you guys are remembering the factor has to do with multiplicative relationship. So we're multiplying. We're using our factors to multiply. So yes, one triangle is smaller than the other. So as before, we're multiplying or dividing. That's our proportional relationship connector, so to say. But when they're asking you guys, look at these two questions. Like, what is the scale factor for ABC, triangle ABC to DEF versus DEF to ABC? So when we are comparing our triangles, we can compare them in different order. So we would say, for example, that this smaller triangle ABC has the value of 2. Large triangle DEF has a value of 3. This is where we got these numbers from. This is your DEF, and this is your ABC. So definitely it is smaller, so the scale factor is 2/3. So triangle ABC is 2/3 of DEF, 2/3 of DEF. And so when you go backwards, the ratio would be 3:2 or 3:2. And we would say, oh, and sometimes we also could have it in this format. We would say, oh, the triangle DEF is 1.5 times greater. So both of them are the same values. It all depends on which triangle is compared to which triangle. Smaller to larger, so you would say, oh, it's only 2/3 of the size of the larger. If you compare larger to small, you would say it's 1.5 times larger than the other. All right, let's take a look at more examples to determine if we have similar shapes or not. So when you guys are setting up these ratios, please be careful with setting up sides that are related to each other. This is a great example. Question number 6 is a great example where your corresponding sides are not necessarily labeled the same. But I hope you guys are remembering that in example 6, when you have a rectangular shape, parallel sides are congruent. So even though this side is not labeled, even though it's corresponding to 12, 16 would be this label right here if we were to label. All right, let's set up our ratio. 9 to 12 as 12 to 16. Super important. Both of my green sides are in the numerator. Both of my pink sides are in denominator. I'm double checking that my proportion is set up correctly. So it won't matter where you're placing it. They just have to match up in that way. All right, I'm going to find my cross products, and I will have 144 as the product of both cross multiplication. So I do have proportional relationship, aka I have a similar shapes. Okay, number 8 would be the next one. I wanted to go over this example again because it does have decimal values. So 3 is in the same position as 4.5. And then I'll label it a little bit differently. So when you guys are labeling, you guys are absolutely in charge as to how you would like for these sides to be labeled. But when I'm setting up my proportion, I am really making sure that my labels match up. So 3 to 1.5, so this is the measures of my smaller parallelogram, are related to 4.5. So 3 and 4.5 are both in the numerator. They're both in pink, related to 3. All right, so we are trying to see if they are in proportional relationship. So for this, I do want to remind you that once again, we can use this relationship, multiplicative relationship, to see if we have a relationship. So we have a pattern, an easy one to spot times. 1.5 times 2 gives you 3. However, from here you are seeing, well, that does not work for my numerator value. So that tells you that this is not a proportional relationship. So you would say these are not similar shapes. They might look similar. They both are same type of shape, but they're not similar shape according to our characteristics. All right, let's take a look, guys, at a second part of your note where we are going to be looking for missing value. So our proportions are really handy. They are going to let us find the missing value. We have done this before with traditional proportions, and so we are using the same properties. So we're going to be setting our proportions and solving them. As before, guys, take a moment to label your corresponding sides. They do not necessarily have to be this colorful, but I wanted to make sure that you are helping yourself to have a wonderful, correct, clean workspace where you're not making any mistakes. X to 4, this is my first ratio. 4 to 2 is my second ratio. I'm spotting my relationship right here. 4 divided by 2 gives me 2. What value divided by 2 will give me 4? X equaling 8. And I can double check this. 8 over 4, 4 over 2. Several ways to check your work. All right, at this point, guys, I would like for you to pause the video and label and set up. So label and set up questions number 11 and 12. All right, guys, hopefully you have the same markings on your paper. And so just double check. I made sure that my 16 and 10, even though they were kind of upside down, both of them are labeled in pink and both of them in the same position. And again, you could have it in denominator. It's not a big deal. X and 6 are both in pink and they both are in the same position. Okay. All right. Let's pause your video one more time, guys. And I would like for you to go ahead and solve these proportions to find the two missing values. All right, so you guys should have X equaling 5 for question number 11 and X equaling 4 for question number 12. Please make sure you guys have this note ready. As you practice, please pick a couple of ways to